Hello everybody, in this lecture we will be solving 1989 IMO problem number 4. Here is a view of this problem. A convex quadrilateral ABCD has sides AB, AD, BC which satisfy this condition here. AB namely is equal to AD plus BC, and then we claim there exists a point P inside the quadrilateral at a distance h from the line CD, such that this relation and this relation holds. If such a point P exists, then we can show that we need to show basically that this condition here holds. Okay, so in order to make sense of this, I will construct the quadrilateral very carefully, and here I have a sketch already. So the condition AB is equal to AD plus BC, what it means is that I start with a circle centered at point A with radius r sub A is equal to AD, and similarly I draw a circle centered at point B, and so that's omega B, and the radius of this circle is simply equal to BC. So these two circles, they intersect here at this point. They are sorry for that, oops. So they are the circles are tangent here, and the point P also given in the problem. By the condition of the problem, P must be such that H plus AD, H is the radius of this third circle, so this point here is P. In fact, let me try to be really careful here, because the space here is very important. Okay, so in fact, let me go ahead and just expand this picture as much as I can. So the point P, the point P is here. Oh, I forgot to change it back. So this is the point P. So, and such that by the condition of the problem, AP is equal to H plus AD. In fact, let's just write it down here. AP is equal to H plus AD. So the point D is somewhere on the first circle, omega A, and the point C is somewhere on the circle, omega B. So AP being equal to, so AP we understand is this line, which so I can simply draw this line here. That's the line AP, and AP is equal to H plus AD. Because D is anywhere on omega A, that obviously satisfies it, right? So H is but at the same time, H is the distance from point P to the line BC. So I will be drawing it very carefully, actually. Next is also we know that BP, I should say, BP must be equal to H plus by the condition BP is equal to H plus BC as well. Now let's identify the location of the points C and D. For this, I will be drawing this line. So what I will do is I will locate the tangency point. So let's say that that's the tangency of CD with this green circle centered at point P. As a result, let's see, it is slightly sloped, I would say, like that, and like that. So therefore, there are two candidates. Oops, sorry for that. So probably something like this would be better. So we have two candidates for point D. Let's call them D1 and D2 here. And there's also two candidates for point C, namely C1 and C2 here. But this is 90 degrees, as you can see, and Well, yeah, that's a beautiful construction then. So you can also be observant that notice that the largest that this green circle can become would be such that it should be inside the quadrilateral EABF, right? Otherwise, so this green circle has radius h, and this distance here is AD here, and we can in a similar way, getting the green color again, if I connect this point with this, again we have this point, this distance is h, and this distance is BC. So therefore point C is one of them, either C1 or C2, two choices, and in a similar way point D has two choices as well. Now consider a fourth circle, and this one is hard to draw, but I will try it. This fourth circle will be tangent to circle omega A and omega B, but it will be also tangent to EF. It is kind of like the limiting case for the green circle, so the largest that the green circle can get. So let me try to draw this circle. Let's assume that it will be tangent to EF at this point here. Actually, let's draw it with the black. Okay, so let's say that this is the point of tangency of this circle, and our circle will look like this. Okay, I'll do my best, but I don't want to mess up my picture too much. Yeah, so something like that, I would say. So, and the center of that circle, let's assume, is somewhere here, and this is the point Q, let's say. So the point Q is the center of that fourth circle, which is tangent to circle omega A and omega B, as well as the tangent line, the common chord, the common tangency chord of omega A and omega B. Circles omega A and omega B. It is obvious that the radius of this new circle, let's call the radius as R of Q, RQ is definitely greater than or equal to H. As I said earlier, the feet of the perpendicular from the point Q to the tangency EF is the point M. In a similar way, I will draw the perpendiculars here and here. Notice that, so you have K here and L here. Notice that KL, and let's write that down as well, KL is parallel to EF. And however, line CD is not such a thing, right? So CD is not parallel. Finally, I will also drop a perpendicular from N, sorry, from the point B to the line AE, and I will call that point as N. So that's also, oops, sorry for that. So that's the point N, and as a result we have another parallel line, NB. NB is also parallel to these other two lines. So now we have some right triangles, and we can compute some lengths. Namely, I need to compute the lengths, the following. Yeah, let's do it here, I guess. I need to compute the length KQ, QL, and BN, making use of the right triangles. For instance, AKQ. If I focus on this triangle AKQ, so let's do it. So KQ is simply the square root of the hypotenuse square minus KA square, right? So that would be the hypotenuse, which is AQ, but AQ is simply the radius of the first circle, which is RA plus R4. So it is just RA plus R, I think we called it RQ, right? RQ. RA plus RQ squared minus, and the distance AK is simply equal to, again, RA minus, so this whole thing is RA minus RQ again. RA minus RQ squared. In a similar way, it's possible to express QL as well. For QL, you can focus on right triangle BLQ. As a result, we would get that RB plus RQ, that's a Q, squared minus RB minus RQ squared, and finally Bn is equal to, again, if we focus on right triangle A and B, so that would be simply equal to, so this distance here is just RA minus RB, and the hypotenuse, this one is RA, this one is RB, RA plus RB, so therefore we get RA plus RB squared minus RA minus RB squared. Now we can play with these. So if you just expand and you, for instance, RA squares will cancel, RQ squares will cancel, what will remain on the for the first one would be 4 times RA RQ, which is just 2 times square root RA RQ. In a similar way, this one would be equal to 2 times square root of RB RQ, and this one would come out as 2 times square root of RARB. But now notice that KL, which is equal to KQ plus QL, is simply the same thing as NB, because we have a rectangle here, right? So we have, let's write that down. Maybe I can write it here. KNBL is a rectangle. As such, we have KL is equal to NB, but KL can be written as KQ plus QL. So KQ plus QL is equal to NB. Now, by just plugging in these values, so what it implies is that this implies that so adding the first two expressions, I should get to the second one. So we have square root RA RQ plus square root RB RQ is equal to square root RA RB. Now I can simply divide across the board by RA RB RQ, so that would then divide by square root RA RB RQ, that's a Q, so we get that 1 over yeah, so 1 over RQ, so we have square root of RB here plus 1 over square root of RA, right, and that's equal to 1 over square root of RQ. But we have established early on that this is RQ, remember, was greater than H. That implies that 1 over RQ is less than or equal to 1 over H, and similarly 1 over square root of RQ is less than or equal to 1 over square root of H, suggesting that this is less than or equal to 1 over square root of H, and that is the desired result that the question was asking for. So that solves our problem, and hope to see you guys in the next in our next lecture.